Hello everyone. Here's the second part for the chapter 2. And you guys have seen how the cathode rays, which means electrons, were found. And also we had seen the charge of the electron and the mass of the electron. And here this experiment shows how they found the atomic nucleus. Okay, remember it was thought that the electrons are embedded in a plum pudding model where the positive body and then you have electrons as plums, but then it was proven wrong from this experiment, which is the alpha scattering experiment and discovery of the atomic nucleus. Okay, so let's go ahead and watch a video about this experiment.
The mystery of how the electrons fitted inside the atom was eventually solved here in Manchester, in this building in 1911, by Ernest Rutherford. Rutherford was, in my opinion, one of the first proper particle physicists because he used beams of particles as projectiles to explore the structure of matter. Now, of course, in Rutherford's day, there was no such thing as a particle accelerator. So he used the decay of radioactive elements to produce his beams of particles. This is Rutherford's original desk. And in fact, if you hunt around a little bit, you can detect traces of radioactivity 100 years later. Rutherford asked two of his students, Hans Geiger and Ernest Marsden, to fire some alpha particles at a piece of thin gold foil and see what happened. So imagine these tennis balls are the alpha particles. Now if the atom were, as Thomson had suggested, a kind of amorphous blob, then you'd expect the alpha particles to pass right through. And that's indeed what happened to most of them. But to their surprise, they found that around 1 in 8,000 bounced right back. After 2 years of puzzling over the meaning of these results, Rutherford realised that in order for the alpha particles to bounce back, they must hit something small and dense. So his new model of the atom was a bit like the solar system, with all the mass concentrated at the centre and the electrons orbiting like planets around the sun. Today we know that this picture isn't quite correct. Quantum mechanics tells us that we can't know precisely where the electrons are, but we can predict that they reside in distinct shells around the nucleus.
Rutherford's alpha particle scattering experiment was remarkably direct and simple, and it showed the nature of what the atomic structure is. By the way the alpha particles bounce off the atom, he worked out where the positive charge of the atom lives.
Rutherford had come to the astonishing conclusion that most of the atom, and therefore most of what we think of as ordinary matter, is in fact empty space. So this apple with the atomic nucleus, the electrons would be a kilometre away. After discovering the nucleus, Rutherford continued doing experiments, firing particles at different targets to delve into the structure of the nucleus itself. By 1932, Rutherford and his colleague James Chadwick had found that the nucleus is made of two kinds of particles, positively charged protons and electrically neutral neutrons.
The discovery in these experiments of neutrons, uncharged atoms of mass 1, has proved of great significance and importance, and has given us a much clearer understanding of the actual structure of nuclei.
Okay, that's the discovery of the atomic nucleus. Excuse me. So this is the experiment that Rutherford had done. There was a thin gold foil and it was bombarded by alpha particles. Radioactive sample emits beams of alpha particles. Alpha particles are positively charged and some of the alpha particles bounced back. Okay, so you can see major deflections in very rarely, and most of the alpha particles went through. Okay, So since alpha particles are positive and then the nucleus also has positive substance in it, when it hit the nucleus it bounces back because positive repels. But most of the time alpha particles went through, meaning that there is an empty space inside the atom. Okay. A particle strikes zinc sulfide screen and produces flashes, and no deflection seen most often. Minor deflection seen occasionally. So that helped to find where the nucleus is located and where the positive charges are located and how far the electrons are away from the nucleus. Okay. Okay. So these are the general features of the atom. Atom is an electrically neutral spherical entity composed of a positively charged central nucleus surrounded by one or more negatively charged electrons. The atomic nucleus consists of protons and neutrons. So we have protons and neutrons in the nucleus and the electrons are in the outer shells or outside. Okay. We have a tiny nucleus and then electrons, they are negatively charged. And protons are positively charged, and since we have the same number of protons and same number of electrons in a neutral atom, there are no charge in a neutral atom. These are the properties of three key subatomic particles. Proton is positively charged, relative charge is +1, but the absolute charge is 1.60218 into 10 to the negative 19. That is absolute charge, positive 1.602. And then for the relative atomic mass unit for a proton, 1.00727, absolute mass is 1.67262 into 10 to the negative 24. Very, very light. Okay, but we consider it as relative atomic mass as 1. Location in the atom is the nucleus. Neutron, it doesn't have a mass. Neutron does have a mass, but it doesn't have a relative or absolute charge. Okay, so 0, 0, it has a mass of 1.00866 and absolute mass is similar to mass of the proton. Again, neutron is also located in the nucleus. And if you look at the electron has a -1 charge and it is the opposite of the proton charge. So proton is positive and the same amount electron would be negative. Negative 1.60218 into 10 to the negative 19. Okay. But for our calculations, we use these relative charges. Proton charge is +1, neutron 0 and electron is -1. Relative atomic mass unit for electron is 0.000548858. It is way less compared to the mass of the proton and the neutron. So when you are calculating the mass number for any atom, we do not consider the mass of electron. Okay, it's even more smaller than in mass compared to proton and neutron, and it is located outside the nucleus. So the atomic mass unit in AMU, 1 AMU equals 1.66054 into 10 to the negative 24 grams. It's about this much, same amount, similar. Atomic symbol, number and the mass. Now if X is the atomic symbol of the element, on the top left would be the mass number. Normally the mass is given by the sum of number of protons and the number of neutrons. And Z is going to be the atomic number, which is the number of protons in the nucleus. and n going to be the number of neutrons in the nucleus. Okay, so A, which is the mass number given by Z plus N. Z is the number of protons, N is the number of neutrons. And this is a symbol for carbon. This is how we're going to write it. Carbon 12, 6. 12 being the mass number, 6 being the atomic number. There are 6 protons and 6 neutrons in the nucleus, whereas 6 electrons in the outer shell. And if you look at oxygen, oxygen symbol 16, 8. 8 protons and 8 neutrons. So 8 plus 8 adds up to the mass number 16. And there are 8 electrons in the outside the nucleus. Normally in a neutral atom, number of protons and the number of electrons are the same. And then the atom will become neutral because the charges are the same. Okay. And then we also have isotopes. So what are isotopes? Isotopes are atoms of an element with the same number of protons, but they have different number of neutrons. Isotopes have the same atomic number, but it has a different mass number. Because if the number of neutrons are different, so the mass is going to change. Okay. These are 2 isotopes of uranium. One is uranium 92. 92 is the atomic number. This one also uranium 92. Atomic number, which is the number of protons. But you can see that the mass number changes. 235, 238. Number of electrons are going to be the same, 92, 92, which is in the outside of the nucleus. And then the number of neutrons is going to be 235 minus 92. That is 143 neutrons. And here 238 minus 92, that is 146 neutrons. So they have the same number of protons, which is 92, but they have different numbers of neutrons, and they are called isotopes. Determining the number of subatomic particles in the isotopes of an element. Silicon has 3 naturally occurring isotopes. Silicon 28, 29 and 30. Determine the number of protons, neutrons and electrons in each silicon isotope. Now, in order to solve this problem, you need to refer to the periodic table. So, you need to refer to the periodic table and see where silicon is located and what is the atomic number of silicon. Okay. Once you find the atomic number for the silicon, and that's going to be the number of protons. What is given here? 28. These numbers 28, 29 and 30, they are mass numbers. Once you find the atomic number from the periodic table, you can subtract the atomic number from 28, 29 and 30. That will give you the number of neutrons. So silicon atomic number is 14. Please refer to the periodic table and see if you can see silicon atomic number is 14. If the atomic number is 14, that means it has number of protons are going to be 14. 14, 14. Number of protons doesn't change. Electrons also doesn't change. 14, 14, 14. But the neutrons would be 28 minus 14. This is the mass number, this is the number of protons, so 14 neutrons. And the second isotope, 29 is the mass number, 29 minus 14, 15. 30 minus 14, 16. It's not that hard. Calculating the atomic mass of an element. Normally, the atomic mass is given by considering natural abundance of all isotopes possible. Okay, so silver atomic number is 47, has 2 naturally occurring isotopes. They are silver 107 and silver 109. From the mass spectrometric data provided, calculate the atomic mass of silver. Now the mass spectrometer is an instrument where you can find out for each isotope what is the percent abundance. Okay, so these are given to us. So this is the percent abundance of each isotope. If you take silver 107, one of the isotopes, its mass is given 106.90509, and out of this mass 51.84% is silver 107, and then out of this mass of 108.90476% abundance is 48.16. So we are going to calculate the atomic mass of silver. So we have to take into consideration both of these masses and their percentage out of this. Okay. So how are we going to do that? We're going to find out the mass, atomic mass unit of each isotope, which is given to us, and you multiply it by this percentage, portion of atomic mass from each isotope. And then you add the isotopes together, isotopic proportions together to find the atomic mass, like this. So for the silver 107, you take this number, that is the atomic mass unit, and you multiply it by 51.84% out of 100. So 51.84 divided by 100 will be 0.5184. So you multiply these two. Atomic mass unit of 107 silver is 55.42. Same thing you do for the other one, silver 109. You take the atomic mass unit and then you multiply by the percent abundance. 48.16%, meaning you divide by 100, that will make it 0.4816. You multiply these two and then you add the two. That will give you the atomic mass of silver, 107.87 atomic mass unit. And this is the modern periodic table. Okay, so what do we have in our periodic table? There are lots of blue in the periodic table. All of these blue sections represent metals in the periodic table. Do you see this zigzag line over here, that dark line? That separates metals from non-metals. So all of these, the left side consists metals, and then the right side consists non-metals along this zigzag line. And these, some of these atoms that lies along this zigzag line have both metals and non-metal characters, and we call them as metalloids. So the green one, metalloids, boron, silicon, germanium, arsenic, antimony, tellurium, they are metalloids. They have both metal and non-metal characters. Okay. And out of the blue section also, you can see there are several shades of blue. So this is one blue, and it's the same blue here. And this section is a different blue. And this section is a different blue. So out of the metals, we have different categories of metals. Okay. So these metals, where you have, we call them as groups. So in the periodic table, these columns are named as groups. So this is group 1, group 2, and then we have group 3, 4, 5, 6, 7, 8. So these two sections, this section and this section, we call them as main group elements. Do you see that? Main group elements, main group elements. Okay. So these are called main group elements metals. Group 1, 2 and group 3, 4, 5, 6. So these are main group elements. And in between the main group elements, so this is 1, 2, A. So these are labeled as 1A, 2A, 3A. 4A, 5A, 6A, 7A, 8A for the main groups. And here it starts 1, 2, 3 and they are labeled as 3B. 3B, 4B, 5B, 6B, 7B, and then here to here 8B. And under 8B also you have 8, 9, 10, 11, 12. Don't worry too much about how the groups are numbered. What you need to remember is excuse me, which ones are the main groups. So these first two columns and this section are main group elements, and these are main group metals. And in between this section we call them as transition metals. Okay, they are called transition metals. And then under the transition metal, from 57 to 72, 58 start from here, after 57, 58 to 71, and in the last row 89 comes 90, 90 to 103, and these are called inner transition elements. Okay, if these were also put here, then the periodic table will become too long, so because of that they are underneath here, labeled as inner transition elements. Okay, and the hydrogen is here. It's being atomic number 1 placed in the side of the metals, but hydrogen is a non-metal. It's not a metal even though it's in the metal side. Okay, so those are the types of elements in the periodic table. So these are columns and we call them as groups, and these rows are labeled as periods. So how many periods are there in the periodic table? Period 1, 2, 3, 4, 5, 6, 7. So there are 7 periods in the periodic table. These are the characteristics. So the how they look. Some metals, metalloids and non-metals. Metals are normally solids. You can see chromium, copper, cadmium, lead, bismuth. They are all solids, most of the metals. And then the metalloids, we call them as semi-solids. They are not as hard as metals. Boron, silicon, arsenic, antimony, tellurium, they are soft solids. Okay, and then if you look at the non-metals, the yellow stuff, you can see some of them are gases, some of them are liquid. And then sulfur is also very it's a solid, but it's again a soft solid. It's not as hard as metals. Okay, for each of the following Z values, meaning atomic number values, give the name, symbol and group and period numbers of the element and classify it as a main group metal, transition metal, inner transition metal, non-metal or metalloid. Okay, so we have to refer to the periodic table, and it's given to us Z equals 38. So let's go to the periodic table and see what is 38. So where is 38? 38 is Sr. Sr is strontium. So what is strontium? What is it? It's a metal, metalloid, non-metal, or transition or inner transition. It's a metal because it's in the blue section, this section. It's a metal. And strontium is in which period? It's in period 5. And which group? It's in group 2A, and it's a metal. Okay. What's the other one? So strontium in group 2A in the periodic table, period 5, and it's a main group metal. And then the next one, atomic number 17. So let's go and look at what 17. So 17, atomic number 17 is chlorine. What is it? It's a non-metal, right? It's a non-metal. What's the group number? Group number This is group number 7A. What's the period? Period going to be 1, first period, second, third. So it's in the third period and group number 7A, and it is a non-metal. And then you have atomic number 27. So 27, again you can refer to the periodic table and figure out where the 27. So here it is 27. It's cobalt. Now what is it? Is it a metal, metalloid, non-metal, transition metal? So cobalt is a transition metal. It's a metal and it's a transition metal. So what's the period cobalt in? It's in the fourth period. And what is the group number? That is under 8B9. Okay, that is the group number for cobalt. (8B9) period 4, and it's a transition metal. Okay. The formation of an ionic compound. So you may have already known that we have two types of compounds that can be formed. Some are called ionic compounds and then some are called covalent compounds. So this is how the ionic compound is being formed. Transferring electrons from the atoms of one element to those of another results in an ionic compound. So ionic compound is being formed by transferring electrons. Normally, ionic compound is formed between a metal and a non-metal. Okay, ionic compound is formed between a metal and a non-metal. Now you know where the metals in the periodic table and you know where the non-metals in the periodic table. Metal will be left side of the zigzag line, non-metals would be right side of the zigzag line. Okay. This is how the sodium chloride forms. So sodium is in group 1 and chlorine is in group 7, 7A, right? Sodium is a metal and chlorine is a non-metal. This is how they see in the macroscopic level. Okay, and this is the elemental or the atomic wave. Sodium atoms and the chlorine exist as a diatomic molecule. Okay, so sodium, if you look at the sodium in the periodic table, you will find sodium atomic number is 11. If the atomic number is 11, it has 11 number of protons and also it has 11 electrons. And sodium mass number is 23, meaning it has 12 neutrons. Okay, so this is the number of electrons and the protons and the neutrons for the sodium. And for the chlorine, if you look at chlorine, atomic number 17. So number of protons 17, number of electrons also going to be 17. And then the mass of chlorine is 35.45. So you subtract 17 excuse me, from 35, it would be 18 neutrons. Basically, a neutral atom will have the same number of electrons and same number of protons. Now, ionic compound is formed by transferring electrons. So where are the electrons? So the electrons are going to be outside of the nucleus. Nothing will happen to the protons. Protons are in the nucleus. We are not going to talk about nuclear chemistry. There would be explosion, right? We're going to talk about that in general chemistry too. So here everything happens due to the transfer of electrons. So out of the 11 electrons in sodium, it's going to give 1 electron to chlorine. So 1 electron, you see sodium atom loses 1 electron. If sodium loses 1 electron out of the 11, how many excuse me, how many electrons would be left in sodium? It would be 10. Easy math, right? 11 minus 1 will make it 10 electrons. So then what's going to be the charge of the sodium if it loses an electron? Remember earlier, sodium has 11 protons, 11 electrons, right? 11 electrons, 11 protons. Electrons are negatively charged, protons are positively charged. So the charges are neutral. Right? So it has a neutral charge, but once one electron is lost, sodium has 10 electrons and sodium also has 11 protons. So protons are positively charged, electrons are negative. So you have negative 10 and positive 11. What's the sum going to be? Positive 1. Right? So that's why once you lose an electron, nucleus or the atom become positively charged because it lost electrons. It has more protons now. Okay, so sodium would be +1. Excuse me. And then the chlorine is taking an electron from the sodium. So to begin with, chlorine has 17 electrons and it has 17 protons. Okay, it has 17 electrons and 17 protons, same number of protons. Why this thing doesn't erase? I want to erase. Did it get stuck here? Come on. Okay, good. So you see here 17 protons and 17 electrons. It's a neutral molecule, neutral atom. Now what happened when chlorine take one electron? How many electrons are going to be there if it take one electron? It takes one electron. So then the chlorine will have 18 electrons and 17 protons. And electrons are negatively charged, protons are positively charged. So what's going to be the sum? -18, +17, -1, right? So then the chlorine will become Cl-1 because it carries a -1 charge. And then, so this is -1, sodium would be +1. By losing an electron, atom become positively charged. If you gain an electron, the atom will become -1 charge. So it loses, so transfer electrons. Sodium transfer one electron to chlorine and chlorine gain one electron. Okay, so that's how an ionic compound is being formed. Now these ionic bonds that form, their strength depend on the charge and the size of the atoms. Okay, factors that influence the strength of ionic bonding. If you have a higher charge like +2, -2, attraction increases. And also as the size decreases, attraction increases. We will learn later on the trends in the periodic table. As you go down the periodic table, size increases. So attraction increases as the size decreases. So if you have a bigger size atoms compared to the smaller size atoms with the same charge, this would have much more interaction between the atoms compared to the larger atoms. Okay, and similarly if you have a bigger charge like 2 plus and 2 minus, there would be more attracted to each other compared to +1 and -1. And again, as the size decreases, interaction increases and the attraction increases. Now I talked to you about that the sodium lose one electron, chlorine gain one electron. Okay, and how an atom decide how many electrons need to lose or gain? That depend on the nearest noble gas to that atom. Okay, the relationship between ions formed and the nearest noble gas. Now you have to refer to the periodic table again. So these are the noble gases. Now helium has 2 electrons and neon has 10 electrons, and argon has 18, krypton 32, and xenon I don't remember. Okay, so when the atoms lose or gain, they want to resemble the noble gas configuration. For example, lithium is in group 1. Okay, so group 1, and lithium has 3 electrons. So lithium will lose 1 electron and become lithium plus 1, meaning now it has 2 electrons which resemble the nearest noble gas to lithium, which is helium. Helium has only 2 electrons. Okay, and then if you look at sodium, sodium atomic number is 11, neon atomic number is 10. So sodium will lose 1 electron. If you lose 1, it would become 10, and that would resemble the same electron configuration or the number of electrons as the neon. Sodium will never become neon, but sodium will have same electron configuration as neon, and that has an added stability. That's why they are called noble gases and or inert gases. So the other atoms, when they lose or gain electrons, they also want to resemble these noble gas configurations. Then it has an added stability. Okay, we will learn later on why they want to do like that, because it's becoming difficult to remove electrons. It has more, we need to give more energy if you need to lose more electrons. Okay, and then if you look at group 2, an element magnesium. Magnesium atomic number is 12, and the closest noble gas to magnesium is neon. This is 10, this is 12. So magnesium, when it forms a compound, it would lose 2 electrons and become 10 electron, which resemble neon gas configuration. And aluminum group number 3A, atomic number 13. So neon has 10. Aluminum will lose 3 electrons and become aluminum 3 plus to look like neon. Okay, so it is the same for the other elements in the periodic table too, and this is for the metals. And if you look at the non-metals, fluorine is right before neon. Fluorine atomic number 9, neon 10. So fluorine, since it's 9, if it gain 1 electron, it would become 10 electrons, right? This would resemble neon. So fluorine will become F minus. That's the most common ion fluorine going to form, F minus. And oxygen, atomic number 8. Closest noble gas, atomic number 10. So the oxygen will gain 2 electrons. If oxygen gains 2 electrons, it would become O2 minus. So the most common ion oxygen makes is O2 minus. Similarly, nitrogen, atomic number 7. So it will take 3 electrons and become N3 minus to resemble neon electron configuration. Same thing for hydrogen. Hydrogen has 1 electron. If you take 1 more, it becomes H minus. Now it has 2, which is similar to helium, which has 2 electrons. So the other elements also gain electrons to resemble the closest noble gas configuration. Okay. Okay. What monoatomic ions would you expect the following elements to form? First we need to figure out where the iodine located in the periodic table. So iodine is 53. So if you look at the periodic table, let's go to look the periodic table. Iodine 53. So iodine is right here. Over here. You see iodine? It's in group 7A. Now, what do you think the most common iodide is going to form? Is it going to lose electrons or gain electron? The closest noble gas to iodine is xenon. This is 53, this is 54. How can iodide become 54? This is 53 electrons, this is 54. It has to gain an electron, correct? So iodide want to gain one electron. If it gains an electron, it would become I minus 1. So the common ion iodide make is I minus 1. And then the other element it talks about is the calcium. Okay, so we have calcium right here, 20. And what's the closest noble gas for calcium? So all of our noble gases are in this column right here. What's the closest noble gas for calcium? Calcium atomic number is 20. So this is 36, this is 18. What is it close to? Is it close to 36 or 18? 18, right? Calcium has 20 electrons and it wants to resemble argon, 18. So what does calcium need to do? Gain electrons or lose electrons? It needs to lose 2 electrons. If it loses electrons, 2 electrons, now it has 18 electrons, calcium. And how many protons? 20. So protons are positively charged, plus 20 minus 18, making calcium 2 plus charge. So calcium will make 2 plus charge to resemble argon configuration. Okay. And I don't remember the third one, but we can go and see. Aluminum. Aluminum atomic number 13. So I'll show you how to look it up. Aluminum over here, 13, right there. What's the closest noble gas for aluminum? There are 2 noble gases. One is argon, one is neon. Which one aluminum is more closer? This is 13. Going 13 to 10 or 13 to 18 is more closer. 13 is more closer to 10, neon, right? And aluminum is a metal. Metals would lose electrons and form cations, meaning positively charged ions. So, if aluminum lose 3 electrons, it's going to have only 10 electrons. And it would still have 13 protons. So what would be the charge of the aluminum if it loses 3 and become neon-like configuration? Aluminum would be plus 3. Okay. Yes. Aluminum would be plus 3. And let's see how much. Okay, let me see. I think we can go ahead and talk about formation of covalent compounds. Now we learn how to form ionic compounds, and that is between metals and nonmetals. Now let's see how a covalent bond is being formed. Normally the covalent bonds are formed between nonmetals, and this is an example how the hydrogen molecule is being formed. Okay, covalent bonds form when elements share electrons, which usually occurs between nonmetals. So this is two hydrogen atoms, each hydrogen carrying one proton, one electron, one proton, one electron. And then they come close to each other. As they come close to each other, proton in one nucleus attracted to the electron in the other nucleus, and same thing happened between the other two. And when they come to optimum distance, they form the bond. Okay, optimum distance is the hydrogen molecule forms because attraction, there is a attraction, the green arrow balances repulsion, red arrows. If we try to come more closer, proton in the nucleus will have a repulsion, electron will also have a repulsion. But once the hydrogen molecule is being formed, it overcomes the repulsion, and at the optimum distance, hydrogen molecule is being formed. Okay, by sharing two electrons. Molecules and ions. Molecule, the basic unit of a molecular element or covalent compound, consisting of two or more atoms bonded by the sharing of electrons. Most covalent substances consist of molecules. We can use this term molecule for covalent compounds. And then we have ions. Ion is a single atom. You can have a single atom ion like sodium ion, potassium ion. So you can have sodium positively 1 and chloride. So these are single atom. Or it could be covalently bonded group of atoms like carbonate, CO3 2-. So carbon and oxygen covalently bonded, but it has an overall charge 2-. We call this also as an ion. Okay, has an overall electrical charge. There are no molecules in an ionic compound. If it is ionic compound, we don't call them as molecules. So these are some of the elements that occur as molecules. Hydrogen, diatomic molecule, covalently bonded by sharing electrons. Nitrogen, oxygen, fluorine, chlorine, bromine, iodine, all of these are diatomic molecules. There are 7, 1, 2, 3, 4, 5, 6, 7. And then phosphorus, tetratomic molecule. Sulfur and selenium, they are octaatomic molecules. Now, if you remember the molecular formula for calcium carbonate, that is CaCO3, calcium carbonate. And this calcium carbonate is being formed by calcium ions, calcium 2 plus ion, and carbonate, -3 ion. Okay, so this is calcium carbonate, and it is formed by calcium ions. So these blue ones are calcium and carbonate. This is carbon and 3 oxygen. They are going to work as 2 units, calcium ion and carbonate. And then the carbonate, carbon and oxygen, doesn't break to individual carbon atoms and oxygen. They're going to remain as a carbonate ion. We call it as a polyatomic ion. Okay, and this is the carbonate ion. A polyatomic ion consists of two or more atoms, covalently bonded together and has an overall charge. In many reactions, the polyatomic ion will remain together as a one unit. They're not going to separate into carbon and oxygen. Okay, so we'll stop here and then we can talk about the chemical formulas in the next session.